that's just large up there. Magic man. Now you say, oh, it just went another way. Nice. All right. But you guys can clearly see that for us to do this by hand would take a long time, right? It's much, much easier to have something that's non-recursive or linear as opposed to having it to be recursive. So any questions about that?
And you said there are two ways. This is the easier, what is the harder way?
One more time.
You said there are two ways you can do it. This is the easier way. What is the harder way?
Well, the harder way is using this.
Oh, okay.
That's what I meant. Like
Just Excel for.
right, and that's why I just used Excel, because I didn't want to sit here and do 10 of those.
Okay.
Okay? All right, guys. So let's take a look at another example. We'll try to. So this time we have 5, 0, negative 5, negative 10, negative 15. So let's just go ahead. We probably need to figure out what D is, and we need to figure out what A sub 1 is. Okay? Both of those are very easy. Guys, what's D in this case?
Negative 5.
Negative 5, because each of them differs by a negative 5. Nice. And then A sub 1, that's just 5, isn't it, guys? That's obvious to see. So if I was to ask you guys for a recursive sequence for this, okay, what would A sub n be equal to in the recursive form?
e to the n minus 1 minus 5.
Nice. A sub n minus 1 minus 5. Good break. Does that make sense to everybody, guys? It's always A sub n minus 1, then you just add the common difference, okay? Everybody in class can do that. Now, it's easy to do that, but it's not efficient to do that, okay? What's much more efficient for us is to use the closed form method, okay? So remember our formula. We just take A sub n, or we just take A sub 1, plus the common difference, which is negative 5 times n minus 1. So, is that right with everybody, guys? Any questions about that? All you do is you just take your A sub 1 and you add to it the common difference times n minus 1. We can distribute the negative 5, so I believe we get minus 5n plus 10 to be the closed form for our sequence. Okay.
Can we take out the 5?
Yeah, if you want to go ahead and factor out a 5 or a negative 5, you certainly can, okay? I don't necessarily know if it helps or hurts any, but it just is what it is, okay? But you're not wrong to do that, Donnie. Let's say that, okay? All right, does that make sense to everybody, guys? If I wanted to find the 10th term in the sequence, just like I did in the previous problem, I could either do it recursively, or I could just stick 10 back in for n. So that would be A sub 10 is equal to negative 5 times 10 plus 10. And I think we end up with a negative 40. Is that correct, guys? Sure, why not? Okay. Once again, I'll illustrate using Excel that we could get it using the recursive. Okay. So we said the first term was 5, and this is equal to B sub 1 minus 5. Okay, and then we'll just drag it down to the 10th term, and there we go. We get negative 40. Okay? Either way we want to do it, it works. But again, and I keep saying it over and over and over again, just because it's kind of important, if you guys can do it linearly, much more efficient. Questions I can answer, guys. Okay? That's our arithmetic sequences. Let's take a look at a couple geometric sequences. Okay? So, we clearly see that for this sequence, 5, 15, 45, 135, we're not adding a number to get to the next term, right? I mean, we could add 10, but then all of a sudden we're adding 30, and then we're all of a sudden adding 90. Okay, so 10, 30, 90. That might be difficult for us to generate some sort of pattern for. Okay?
Go up just a little bit.
Oh, what you need? Oh, just go back up a little bit more.
Yeah, that.
Is that good? Okay. So, for this guy, guys, we're using the geometric relationship, okay? And you guys have your formula for the geometric relationship. So, once again, we need not D this time, but we need R, and then we need an initial value. Okay. So, guys, clearly in this example, what's R going to be? 3, right? The common ratio is 3. Each successive term, we're multiplying, or each successive iteration, we're multiplying by 3. And then clearly the initial value is 5. Okay, we're hopefully clear. So, if I wanted to get the recursive definition for this, A sub n, okay, we look back now not at our definition for arithmetic, but now geometric. Okay, let me scroll back up to that just to make sure we're okay with this. Okay, And all you do is you take the initial value and multiply it by r to the n minus 1, okay? So, or for the recursive, it's just r times a sub n minus 1, all right? So, for this one, it would be 3a sub n minus 1. So, does that make sense to everybody, guys? All we're doing is we're just taking the common ratio, multiplying it by the previous iteration, and that'll give us the next iteration. For letter B, okay, now this is the one that's more important to us, especially if we want the 10th term in the sequence, okay? That's going to be equal to, what do we say, the initial value, which was 5, times the common ratio, which is 3 to the n minus 1 power. Okay. Does that make sense to everybody, guys? Any questions about how we substitute those? Okay, it's not difficult, it just is what it is. Now, of course, what we'd like to do is we'd like to be able to verify that if I was to substitute 10 back in, okay, that I get the same thing both recursively and explicitly for this, okay? So this one we definitely want to have a calculator for, unless we know 3 to the 9th power is times 5 off the top of our head. So a sub 10 is going to be 5 times 3 to the 10 minus 1, okay? Or in other words, 5 times 3 to the 9th. And I don't even know if your calculator will give you a number for this that's not in scientific notation. If it does, let me know. If not,
98415.
was it
98415.
98415? Okay, that's not as ugly as I thought.
Yeah,
Why did I think it was going to be really ugly?
That's 3 to the power 9. That's not that much.
Yeah, it does. It really does, yeah.
It's not.
I guess it's not as bad. Okay. Right. Now, let's see whether or not this actually works. If it actually does give us the iteration that we need. So, we'll do it recursively. Okay, so we'll start out with, I think our initial value is 5, right guys?
Yeah.
And then to get to the next term, we multiply by 3. So it's c sub 1 times 3. Okay, and let's just drag it down to the 10th term. 98415. That's what we got, right guys?
Yes.
Yeah.
Nice, okay. So now we can verify that it works, okay? So that's pretty cool that we can now write it both recursively as well as closed form, okay? So we know that this is the answer, unless we got exceptionally lucky, which we know we're not. Okay, all right, any questions, guys, about that? Okay, last one that we have here, we have a little bit of fraction stuff going on, so it might be a little bit more difficult for us to find R, but hopefully not. So, if I was to ask you guys in this specific sequence what R would be, if I think you might know, 2/3, right guys? And isn't it obvious that if you just pick, let's say you pick 8/3 and 16/9, to go from 8 to 16 you multiply by 2, to go from 3 to 9 you multiply by 3. It doesn't matter which two terms you pick, they have to have the common ratio, okay? So that would be 2/3, and then clearly initial value of a sub 1 is 4. So, for the recursive version of this, okay, recursive version is going to be what, guys?
2/3. Then a sub n minus 1.
Yeah, 2/3 times the previous iteration. Okay. Really easy, right, guys? Not a big deal. Okay. If we wanted, though, to be able to write the closed form of this, that might be a bigger deal. Okay, so we're just going to go ahead and take the initial value, which is 4, and write that as what? 2/3 to the n minus 1, right, guys? We could simplify that, believe it or not. Okay, you guys might not want to simplify it, but we could express it in a different way. Okay, let me illustrate how. Okay. By the way, if you left it like this, I'm okay with it. Yeah, this is okay with me. This is part B, by the way. Okay. But another way you guys, in fact, let me do it over here so I can show you guys. But if we have 4 times 2/3 to the n minus 1, and I wanted to write this in a different manner. Okay. Couldn't I write the 4 as 2 squared? Okay, because that's what 4 is. And couldn't I write this quantity as 2 to the n minus 1 over 3 to the n minus 1, right guys? And now, don't I have a couple base 2's right here that I could combine into a singular base? So, if I was to combine these, okay, what would that combine into? 2 to what
N
power?
plus 1.
N plus 1, okay? Because all we would do is just take this 2 and the negative 1 and we combine it, okay? So another way that we could write this is 2 to the n plus 1 divided by 3 to the n minus 1.
That's way
if we wanted to.
That's way uglier.
I don't know. Not necessarily, because now you don't have a coefficient to work with. Now you have 2 bases to work with. I don't know if it's uglier or better or not. You would probably see this version if you were looking at the back of the book answer, believe it or not. Because they like to have one common base, okay? It's just, it really is easier to work with a singular common base, okay? Whether you guys like it or not. All right. Now, of course, what we want to do is we want to make sure that this works out, okay? So let's go ahead, let's find the 10th term in the sequence, and then let's go ahead and see if Excel likes that using the recursive measure, okay? So, for part C, if we wanted to find a sub 10, okay, that would be 4 times 2/3 to the 10 minus 1, or in other words, 4 times 2/3 to the 9. And I don't know if that's going to give you guys a nice fraction or not, if you use the math enter or not, but did anybody get a nice fraction out of this, or did it just keep it into the, it just put it in decimals? Okay. Greg, what'd you get, sir?
1040, or .1040.
0.1040.
And if you want to do the last one, it would round up to 5.
Okay, that's fine. As long as we get that, I mean, it's pretty obvious that we'd be correct, okay? Excel's obviously only going to give us the decimal answer, so it doesn't hurt my
I did get a
feelings.
fraction though.
You got a fraction?
Yeah, 2048
Uh-huh.
divided by 19683.
Do you have an 89?
There's a 3 after the.
Oh, okay, what is it?
After the 8 in the denominator.
Oh, okay, there's a 3 there. I'm sorry.
Well, you can convert it back and forth, right? That's the thing, so
it doesn't
each calculator will give you a different.
Yeah, it doesn't really matter, quite honestly, you're right.
Actually, what I did was I expanded 2 to the power 9, then multiplied by 4,
Oh, okay,
and
yeah.
then 3 to the power 9.
Okay, so we had, the initial value was what for this, guys, 4? And then we're gonna say that that's gonna be d sub 1 times 2/3, right, guys? Okay, so, let's hope for our 10th term we get 1040. 0.1040, nice, and then you said it rounded to 5, correct? Yeah, that looks like it's gonna work out nicely, so again, just illustrating that we get the same answers regardless, okay? I think it's pretty neat that we can write the same sequence in 2 different manners, okay? Alright, guys, any questions about being able to write either an arithmetic or a geometric sequence into a closed form or into a recursive form? Alright guys, so like we've been saying, okay, this is what we're kind of leading up to. What we'd like to do is if we have something that's recursive, we'd like to be able to write it closed, okay? We can obviously see that closed is much, much, much more efficient than the recursive sequence, okay? So here's how we're going to do this. We're going to use something called the method of iteration, okay? I can't remember. Somebody said that they took differentials already, so, Donnie, and do you remember anything about the series solutions? No, that's okay, I won't remind you. When you guys are taking differentials, you actually use this to be able to get a closed form of a series, okay? So this is something that some of you guys, in fact, have you guys gotten to Taylor and Maclaurin series yet in Calc 2 for those guys that are taking it? Have you guys gotten to the problems where you actually have to go through and just keep iterating it to find a closed form yet, or not yet? Okay, because there are ways to be able to write them in closed form and you just kind of have to guess it, okay? Maybe your teacher might not even make you do it, okay? I always make my students do it, but regardless. So anyway, what we're going to do is we're just going to keep writing out the terms of the recursive relationship, and then hopefully what we can do is we can be able to verify what, some sort of closed form for this, okay? So the first couple are pretty easy, and then they start getting really difficult after that, okay? So we might only do like maybe the first 2 or 3 today, and then next time we'll finish up the rest of these, right? So let's start off with one that's pretty easy, okay? So we have this recursive relationship. A sub k equals k times a sub k minus 1, a sub 0 is 1, and k is bigger than or equal to 1, Okay, so let's just start writing out the iterations for this. Alright, so for the first one, I don't know what's going on here, I don't like it though. There we go. Be gone. So the initial value, no, not gone, that's okay, we'll just do it on the whiteboard. You guys don't have this electronic problem on your papers. Yeah, this looks like it's gonna be fairly ugly, but it's actually gonna work out really nicely. Okay, so we said a sub 0 is equal to 1. Right. If I asked you what a sub 1 is, in other words, what's the next iteration in this sequence, okay? Can somebody tell me what that would look like?
Yeah, that should be like k is 1, right?
Yep, k is 1, because
So
that's the
1
subscript, so 1 times
times
1,
1, yeah.
right guys? And by multivariable calculus methods, 1 times 1 is 1. Okay, well that's nice, okay? Now, what about a sub 2?
2 times 1.
Okay,
Two,
or
1
wouldn't
times
that
2.
be 2 times 1 times 1, right guys?
Yeah.
Just because it's the same thing as the previous iteration, okay? So what I like to do is I like to use the previous iterations to maybe get a better sense as to what's going on with this. If you did 2 times 1, you might be able to see the answer, but I think this might give you a clearer picture as to how we're going to progress with this. Okay? Now clearly, 2 times 1 is just 2. So it's not looking like it's doing too much with this. Okay? A sub 3. Okay? A sub 3 is going to be what, guys?
2 times,
2 times 1 times
3 times 2 times 1 times 1, right guys?
Mhm.
So all I'm doing is I'm just taking the previous iteration and I'm just sticking that back in. Okay? Does that make sense, guys? That's how a computer would do it, right? Computer doesn't remember the answer, it remembers the elongated form. Okay? So a computer doesn't necessarily do the computations each time until it gets to the end. That's why recursion is extremely expensive, because sometimes the computer doesn't